Okay, students, this is session number 26 on industrial metallurgy, and we'll continue our discussion on type 2 systems. This is what we are going to cover in this particular session. Mainly, we'll see how do we construct the equilibrium diagram of bismuth cadmium alloy systems as an example of type 2 systems. Okay, and finally, we'll show you the neat and labeled bismuth cadmium equilibrium diagram. So we said in the last session that type 2 systems are binary alloys in which the two constituent elements show complete liquid solubility. However, they show zero solid solubility. We also learnt about the reasons why this type of a behavior is shown by a bismuth cadmium alloy system. Uh, you see, again, we'll take the help of thermal analysis technique, the experimental method, to construct the equilibrium diagram, the phase diagram, or the constitutional diagram of bismuth cadmium alloy series. Well, we know that in the use of thermal analysis method, we take a large number of samples, each of different chemical composition, and each of that samples of different chemical composition is taken to a very high temperature so that they get into the molten state. From that molten state, each sample is cooled down under strict conditions of equilibrium, and the changes in temperature with respect to time are noted. And when we have reached the room temperature and we have collected all the data, when we plot this data on the temperature time graphs, we get what are called cooling curves. So like this, we get a series of cooling curves, and here are the cooling curves that I am showing to you. The first we have for pure bismuth. Pure bismuth, being a pure element, solidifies at a single temperature. Its melting temperature is 271 degrees centigrade. Then we come to an alloy of bismuth and cadmium where we have taken 80% bismuth and 20% cadmium. You can see the solidification starts at temperature T1, and then it proceeds and finishes at 144. What is important to note is that a part of the solidification over here is getting completed isothermally, and students, mind it is this isothermal transformation which represents the eutectic reaction that I talked about you in the last slide. So another alloy with 60% bismuth and 40% cadmium. Now this is a special alloy. See, alloys, if I show you the next alloy, alloys would always melt over a range of temperature. Alloys never melt like pure substances at a single temperature. Nickel, see this cadmium, pure cadmium would always melt at a single, solidify at a single temperature. Pure uh, bismuth would always solidify at a single temperature, because these are elemental things, these are pure metals. uh, but so this portion is not correct. This should have been a continuous line like this, as has been shown over here, and this T1 temperature is lower than T3, mind it. So what I'm trying to tell you is that an alloy would always melt, solidify over a range of temperature, but this is a special alloy. As we discussed, this is the eutectic composition of the bismuth cadmium alloy series. This is the eutectic alloy of this bismuth cadmium alloy system, where the entire alloy is melting or during heating, or is solidifying during cooling at a single temperature, and this temperature is called 144, would be referred to as the eutectic temperature of the bismuth cadmium alloy series. So after these cooling curves have been obtained, now we will start the construction of the equilibrium diagram for a binary alloy. Like here we have taken bismuth cadmium. For a binary alloy, we know that equilibrium diagram is between temperature and composition. Temperature is taken along the y-axis, composition of different alloys is taken along the x-axis. We'll draw a blank temperature composition curve, and over that blank temperature composition curve, we'll start transferring the temperatures which were representing the start of solidification for different compositions. So I'll transfer 271 corresponding to 100% bismuth, then T1 corresponding to 80% bismuth, 144 corresponding to 60 bismuth, T3 corresponding to 25 bismuth, and 325 corresponding to 0 bismuth or 100% cadmium. After I have transferred all these points which represented the start of solidification, I'll join all these points and I'll receive what is called the equilibrium liquidus line of the bismuth cadmium alloy series. Next, all temperatures which were representing the end of solidification would be transferred. So 271 again for 100% bismuth, 144 for 20% bismuth, 144 again for 40%, 144 again for 75, 321 for pure cadmium. So like this, all these transfer temperatures would be transferred, and now these were the temperatures which were representing the end of solidification. And when I join these points, I'll obtain a line on the diagram, and that line would be referred to as the solidus line of the bismuth cadmium alloy series. So this is how those points had been transferred, representing the start of solidification. One would have been here, the other over here, the third over here, the fourth over here, and the fifth over here. Similarly, I had points representing the end of solidification, so I joined them, and it is this. So above this, the material system would always be in the form of a liquid solution, homogeneous liquid solution, the liquidus line. So this region is a single phase region, the liquid solution. Then beneath this line, solid phase, solid bismuth, pure bismuth had solidified as a separate solid phase, and somewhere below this line, liquid would have precipitated, because here you had complete liquid. No sooner you reach here, solid cadmium would have solidified out of liquid, and now you are in a two-phase region. And because this is the solidus line, anything below this is complete solid. So we have solid cadmium and solid bismuth. This is a two-phase region. So in this entire diagram, we have one single phase region, and there are three different two-phase regions. And here, students, we have a triple point where you will see liquid solution, you will see cadmium solid, and you will see bismuth solid. So there is one triple point also in this equilibrium diagram. Let me on the next slide show to you the labeled equilibrium diagram for bismuth and cadmium. So this is how it is. You can see ABC is the liquidus line. Then AD, B, E, C. This is the solidus line, means anything below it would always be a solid. Then okay, solid bismuth means pure solidified bismuth. This is pure solidified cadmium, and L means homogeneous liquid solution of bismuth and cadmium. So students, this gives us the neat and labeled. It would be neat because coming on a computer and drawn through with the help of computer aids only, but it's a labeled diagram now. And in the next session now, we'll start discussing the equilibrium cooling of bismuth cadmium binary phase diagrams. And interestingly, in the end, we will prove that this diagram that has been constructed by us with the help of only experimental method, and we haven't checked it yet, is wrong. And then we'll apply the Gibbs phase rule to prove that this is wrong. And then we'll try to find out the reasons that why it has gone wrong. Why did it go wrong in the first place? So that would be something interesting to discuss with you. I have finished with this session. I hope you understood the terms and the other things that were explained to you in this session. Thank you so much for watching.